Today we'll be working through Student Handout 1, titled Simplifying Expressions. The vocabulary is going to be important, so we'll begin with that understanding. An expression is a mathematical phrase that can combine variables, numbers, also called constants, and operations. Below is an algebraic expression, and we're going to label its parts. So the variables in our expression are our letters, and our numbers are what we call our constants. Obviously, this is our operation because this is an addition expression. But I do have another operation that sits right here in what we call a term, which consists of the variable and the coefficient. A fancy name for the number in front of the variable. So, while we're on that, quick review of that understanding. A coefficient can be negative or positive, and also understood to be 1. So if I have a term with a variable with an unseen coefficient, it's understood that that coefficient is 1 because the identity for multiplication is 1, meaning I can multiply x by 1 and still have x. So every variable has a coefficient, whether it be seen or unseen, meaning understood to be 1. Now, filling in our vocabulary, simplifying expressions, terms can be classified as like or unlike. This is important because that helps us know what we can and cannot combine. Terms can be classified as like or unlike, and expressions can be simplified by combining like terms. Like terms must have the same variable. And we're not going to put an and, but I'm going to continue that with raised to the same exponent. For example, 7 times x and 9 times x are like terms. Like terms because they have the same variable raised to the same exponent. Now you might be thinking they don't have an exponent, but if you don't see the exponent, it is understood again to be 1 because 1 is our identity for multiplication, and x to the first power is the same thing as x. So the coefficient doesn't determine like terms. The variable and the exponent does. 7x and 9x are like terms, but 7x squared and 9x are not like terms because of the 2 and the understood 1. 4D and 4G are not like terms, because simply seen, they have 2 different variables. So a like term, got to be the same variable, has to be the same exponent. What we're going to do next is work on recognizing like terms, because those are the ones that we can combine in our expressions. So we're going to take just a moment. I'm going to do a few, then you'll do a few on your own. I am counting 4 terms, 2 positive, 2 negative, and I'm looking for my like terms. To do that, I'm looking for the same variable raised to the same exponent. So I see 8c and negative 8c to be like terms. Skipping, I see 3 terms, 3 positive, an x, nope, that would be a y, a z, and a w. Therefore, I have no like terms. There are none. Skipping, I have 1, 2, 3 terms. 2 contain the same variable raised to the same exponent, so both terms are called like terms. You'll practice the rest in just a moment. In the next chart, they're looking for us, or asking us to write either like or unlike. So notice I've got a 29 and a 29 squared. There is no variable involved. It's just constants or numbers. So this 2 of as an exponent does not need to be considered because there is no variable. So 29 as a quantity and 29 squared as a quantity, a number, would be considered like terms. B and 3b would also be considered like terms. And while we're reviewing, the coefficient in this term is 3, and my coefficient in the term b is 1, simply because 1 times b is b. So again, every variable has a coefficient. Every variable has a coefficient. In 13k and 13k squared, they do have the same variable, but they are not raised to the same exponent. Therefore, these are unlike or not like terms. So take just a moment, pause the video, complete the remainder. Restart the video when all have completed. Take a moment, check your answers. You may need to pause the video for everyone to have time to check. On the back, I dropped them. On the back, we are going to now learn how to combine these like terms. So it's important that we can recognize a like term and unlike terms in our expressions, so we'll know what we can and cannot combine. So basically, only like terms can be combined. The problem below, we will look at how that is done. So the Robinson family ordered snacks at the fair, and they bought the following drinks, the following pizza, and the following number of ice cream cones. So the first thing we're going to do is write an expression to represent the cost. We know that there are 5 pizzas. We also note there are 3 sodas, and there are 2 cones. And if I knew how much each one cost, I could multiply. Say the pizza costs $2, 5 times 2. See how much I'm spending on pizza, and so on. But because I do not, we're going to use a variable to represent that understanding. So I'm buying a pizza, and another pizza, and a soda, and a soda, and a cone, and a pizza, and a cone, and we continue to represent each with our variables. Now, it says to write an expression. Technically, we just did, but what we're going to do is now order that expression so that all of my like terms are grouped. I have 3 sets of like terms. My P's need to be together, my S's, and my C's. So I'm going to, order's not important, often we go alphabetical, so I'm going to start with C plus C plus my pizzas, and we know there's 5. That's 1, 2, 3, 4, 5. So I have 5 pizzas, and I have 3 sodas remaining. To simplify this expression, because it is all addition, there is no subtraction or negative terms, we could just count. But what we want to look at is algebraically, how are we getting a 5 out of these p's? Where is my 5 coming from? Where is my 2 coming from? Mathematically and algebraically. So, what we're going to think about is, what is the coefficient for each one of these variables? And we know that it's 1 because every coefficient has a variable. Well, I kind of said that backwards, but that's a true statement too. And basically every variable has a coefficient. So we know that 1 is the coefficient for each variable. And I say that because to combine and or simplify like terms that contain the same variable, we're going to do so by factoring. We know that when we're multiplying, this is called factor, factor. Factor, factor. I'm just looking at my 2 terms that are C variables. I'm going to factor out that C, and I'm going to sum the coefficient. And that's how I'm going to count or add. 1 plus 1 is 2 cones. And then I'm just going to continue. I'm now looking at the next 5 terms that are like, and they all contain a p. So I'm going to factor out the p, and I'm going to sum the coefficient, which in this case happens to be a 1. 1, 2, 3, 4, 5 pizzas. And last, same process. It works every time. Factor out the common factor, sum the coefficients, and that's going to leave me with 3 sodas. And we are done. We now have simplified our expression to a much simpler, more simple expression, which is 3 terms opposed to 9 terms. And now we're going to practice. Before we do, what I'd like to do is prove this distributive property that we're using here. So kind of running out of room, but that's what I'm using on that step, our distributive property. And what we used here, just to back up, I forgot to label that. What we're using here is the commutative property of addition. So we had the order that I rearranged so that all my terms that were like terms were side by side. And then I used that distributive to help me combine my like terms. So here's a little bit of proof behind that so we'll know what's actually taking place, and that would be this. Let's just say that I have 7 plus 2, not plus, fix that. Let's say I have 7 times 2, and I have 3 times 2. Well, if I'm just focusing on that multiplication, I notice factor, 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 factor. They do have a common factor of 2. So I'm going to claim that I can factor out that 2 and sum the other 2 factors. So basically I went from an addition problem to a multiplication problem. But these 2 are equal. And if we calculate that, because we have all numbers and we can, then I can see that when I follow the order of operations, on either side of the equal sign, I still get 20. Why? Because they are equal. So that's that same concept. Let's just say that I have 7C and 3C. Then what I'm doing And that distributive property is I'm factoring out that common variable and I'm summing the coefficients, which we can continue at this point to get 10c. I can't multiply because I don't know what c is. Here I was able to simplify to a constant because I knew all my numerical values. So that's what we're working on, this process right here. We're going to use that in our examples. So in our first example, we like to count our terms and see how many we have. 1, 2, 3, positive, negative, positive. So we can see that negative term as add the opposite. I'm going to carry down my first term, carry down my third term, and now I'm going to order so that my like terms are left or side by side so I can solve this left to right, and or simplify, I should say. Simplify left to right. I now see that I have the common factor A. I'm going to factor that. And now I'm going to sum the coefficients. Now, and that would be my distributive property. I just ran out of room, so I'm going to put that right here. I'm going to move this down, make this 4. And my final answer would be 15, because I'm summing here, A, just carry it down. And then this right here is what we call that double sign, adding a negative, simplified to subtracting a positive, and you are finished. All right, let's try it again. We'll go down. We'll go ahead and do 4 since I kind of messed that box up. And I count my terms. 1, 2, 3. I notice I have negative, positive, negative. And I also notice that all 3 terms are like terms. So I do not really need to do the commutative property because everything is in order. So I will begin factoring. Or, I notice this subtraction, if you choose, begin factoring, or you could change that to add the opposite. So you can see that negative. Sometimes it matters, it makes a difference, sometimes it does not. But I do see my 3 terms, hence my addition sign in between, and I'm going to now factor. There's my D. Notice this time I have 3, and that's fine. It doesn't matter how many terms you add at one time. I'm summing now the coefficient. I should say combine at one time. So I have 3 add-ins. I notice that -5 and -3 are going to give me -8. That's my additive inverse to +8, so that actually gives me 0. And again, I'm running out of room, so I'm just going to arrow over. And the 0 property tells me I don't need to know what D is. I know that anything times 0 is 0. So we're done. Next, we'll go ahead and continue down the page. Once again, I have 1, 2, 3, 4 terms. Positive. Okay, we have a positive term, negative, positive, negative. So if you want to see that negative term, you can change that to addition of the opposite. So you can see that you have a -3 and a -10. I have 2 like terms, 2 sets of like terms. My variable G and then my 2 constants. I'm going to use my commutative property of addition. My commutative property of addition to reorder so that I can combine my like terms by factoring out that common factor, summing the coefficient. which will leave me with, put my decimal in there. Right, so that right there, if you add that up, it's going to leave you with 8. Carry down the G, and I've got 8 times G. So currently now I have a -10 and a -3, which is going to give me a -13. So for my final simplified expression, I'm going to rewrite that, add a negative to subtract a positive, and then you are done. At this time, I would like for you to pause the video, use the examples, and work the remainder of these problems. Once everyone has completed, resume the video. Take a moment, check your answers. You may need to pause the video to have time to check.